Good afternoon and welcome to the 23rd Annual Exhibit of Hydrogen and Fuel Cell Technologies and Batteries. We've been here for quite some time discussing new developments, and of course it all involves testing these developments and working from testing and R&D through to mature products. We need specialists in this field, and we're going to be talking to one shortly. It's Dr. Ravn Nielsen, who's the Center Manager at DTU Energy, the Fuel Cell Hydrogen Test Center. Please welcome with me Dr. Ravn Nielsen. So, good afternoon.
Good afternoon.
So Ava, question number one for people who don't deal with abbreviations. Well, DTU, what does that stand for and where are you?
Yes. DTU is the Technical University of Denmark. And in Denmark, we educate engineers from Denmark and from most of the world. We have more than 12,000 students, and we have 5,000 staff members. And we have a number of fields that we do engineering about. So most of the technologies you can think of, we have some educations. Last year, we were ranked number 2 in the world concerning energy, science, and engineering, and actually top 1 in Europe, which makes us very proud.
It should, yeah. And you and your department, you have the Department of DTU Energy. What are the activities there specifically?
Yeah, DTU Energy is one of 19 departments that we have at DTU. We deal with a lot of energy technologies. We deal with fuel cells, both PEM and solid oxide fuel cells. We deal with electrolysis, all the kinds that you can think of. We work with photovoltaics, we work with batteries and a number of other technologies. And we focus very much on applied research. So making sure that whatever we deal with will end up as products in the real world. So making a difference and good solutions energy-wise. One way we do this is when the processes we deal with are all industrial scalable processes. So it's not very exotic processes that can never be scaled up. From the beginning, we think, how can this end up being a product, being used? And it's already on the slide here that we have a number, we are more than 230 employees. And we are more than 100 working with fuel cells and electrolysis. So that allows us for being very cross-disciplinary in our approach. So we have very, very skilled colleagues dealing with manufacturing and processing, especially the ceramic processing of ceramic fuel cells and ceramic electrolysis cells. They develop and they produce some of these cells, pass them on to colleagues that do testing and characterization, both electrochemical testing, but also microscopy. And by this we know much about how it was produced, how it performs, and what the microstructure is looking like, because that's very important for the performance. And then we can also rely on modeling. That's the third big discipline in our department. And working on these 3 topics together allows us for very efficient development of fuel cells and other technologies that we deal with. It also says materials, components, and systems, and that's the scale we deal with. From the beginning, we were research department on material science. We have been at Risø, that's the Risø National Laboratory, and since 1987, we have been working on solid oxide fuel cells. It was actually my father, Professor Mogens Mogensen, who started with colleagues in 1987, and also later turned these activities into solid oxide electrolysis R&D. And we have colleagues at the main campus north of Copenhagen. We are at Risø, 40 kilometers away. And next year, we will actually relocate to the main campus where they're at the moment constructing a new building for us, so that we will be closer to the other departments and closer to the engineer students. So we look forward to that.
That all feeds into the interdisciplinary nature of this industry and this technology. For people who haven't been to your stand, which is E57 in that direction, what are you exhibiting this year?
We are here both representing the department, DTU Energy, but as well very much FCH Test Center. I'm center manager of this test center where we offer testing services to industry and other organizations. Since 2010, we have been doing this in terms of the test center, and we provide very much tailor-made analysis, and we have really long experience in the fuel cell testing and data interpretation. So one thing we do is what we call a fingerprint, because that's the very core of the performance of a fuel cell. We test at various temperatures, at various gases, so oxygen and fuel, and then we make impedance spectroscopy, for example, an advanced electrochemical test, and thereby we can say where the degradation takes place, where the internal resistances, in which layers of the cell is responsible for what loss in the cell. Mm-hmm. And this is also something that we feed back to the processing people and get improved products again and again. Mm-hmm.
When I go back in time, it's been quite some time actually, but a few years ago we had the PEM cell testing facilities on stage here. These are really nasty guys. They take a PEM cell with precious metals in it and they dump in a little bit of CO and sulfur and intentionally poison the PEM cell and watch the efficiency of the PEM cell drop and the degradation rise, and it becomes a great mess at the end. What sort of challenges do you present the solid oxide fuel cells with, or what sort of specific conditions related to solid oxide? They have different operating temperatures, they have different pressures, and so on and so forth. So what are the specific challenges in testing a solid oxide fuel cell?
Yes, as you probably know, that the solid oxide fuel cells are very tolerant to impurities. They can stand CO, CO2, even a bit of sulfur is acceptable. And we have in our lab shown several times that how it reacts to sulfur poisoning. It changes the performance a bit when you then again remove the sulfur from the gases. It recovers to the performance that it has had before. So solid oxide fuel cells are very tolerant and compatible with a number of fuels. Any fuel you can think of, you can put into a solid oxide fuel cell. And you can even, in some cases, rely on internal reformation within the fuel cell under operation, and thereby having a simplified system. Mm-hmm. We can also test under high pressure. And one thing we specialize is accelerated testing. A challenge from industry is to predict how long can my product last? What's the lifetime? And it's really difficult to make such projections until you have actually shown that it has been working for 10 years. Then it's a bit difficult to claim upfront that it's going to last 10 years. But we develop accelerated methods, so we do thermal cycling and load cycling, and finding out what the degradation mechanisms are, and thereby do the best forecasting lifetime that is possible.
Solid oxide fuel cells have been on this fair for quite some time. We know them as stationary applications with very successful efficiencies. Their presence I've seen year in, year out. In fact, they're so common right now in industrial applications that they don't need to exhibit every year. People know this technology. What I find so fascinating is the side of electrolysis. The big electrolysis people if you don't include steam reforming, which uses natural gas. The big electrolysis, the suppliers of hydrogen are the PEM electrolysis and the alkali. And rarely have I seen a solid oxide electrolysis unit. This is the big discovery for me this year. These things, it's a viable technology with just fantastic claims of efficiency. So where did this technology come from? Is it really new, or has it made huge advances in the past few years? Suddenly, solid oxide electrolysis is among the greats.
We that have been working with the technology has known for quite some years that solid oxide electrolysis has really high potential and might be the winner of the electrolysis race that is going on now. We really need to scale up and get production costs down by industrial scaling, but the efficiencies are very high, and the costs forecasts are really, really promising. And there's also the feature that our units, or the manufacturer's units, our technology can actually work reversible. So you can have the same unit, the same box, used as a fuel cell and at the same time as an electrolyzer. And we have proved how the performance is again, and actually the degradation is even lower when you alternate between fuel cell mode and electrolysis mode. We have been mimicking real wind energy curves from a Danish island called Ærø. There we have 14 days of wind profiles, and we have applied that to our units and compared it to the needs, electricity needs of the inhabitants in this island. And sometimes, much of the time, there is a surplus of energy. And all that time, the unit is operating as an electrolyzer and producing hydrogen that can be stored for later, or that can be used for other purposes. And then the hours and days where there's not enough wind to cover the electricity needs, then the unit can turn into fuel cell mode and then provide electricity and cover the needs. And it's no problem to follow such curves.
This is, I want to fix this point because it is so important. Among the debates we have with the electrolysis industry is it has to be fast response. That is, when there's a drop in current, the unit doesn't mind that. When the current increases, it doesn't have to go up to maximum. It should start working as soon as there's a flow of current. So this rapid response time, and then when the current is really full blast, it doesn't mind taking that load again. So do solid oxide electrolysis units really compete well with PEM technology?
This is not the technology that will balance the grid on smaller time scale than 1 second, which the electricity grid often needs. I'm not sure that PEM electrolysis is the right balancing technology either. But on a 15-minute scale, which is also very useful, we can easily balance. And if it's installed in large scale, there will also be sufficient or significant impact to balancing an electricity grid. And for the wind profiles, I was thinking when you watch such profiles, it goes up and down, peaks here and valleys there. But actually, the wind does not change over seconds. So it's difficult to predict in detail, but the changes are going on over a quarter of an hour. And our technology can easily follow that. So that's not an issue.
I find this an important issue because we talk about grid stabilization as if fuel cell technology is merely there to stabilize the grid or to supply electrical energy. But in Germany, 15% of the total national energy budget is electrical in its form of consumption. The big pie, what we're trying to chase after is our dependency on fossil fuels for the rest. And this depends on being able to utilize renewable energy, which is being dumped right now. They turn the wind turbines off. You also have a big source of wind energy because we share the north coast. And this is facing a far larger prospect. That is, the business model for electrolysis is enormous if you can recover that energy, but you have to be able to use it. And here's the debate. Do we ship all of this hydrogen down to the south, or do we build electrical cables here? What I find so fascinating is a reversible unit does both. Rather than paying the price of two separate units, and you can make this into a sort of desegregated grid. You can, wherever the wind power is created, you can have units in several locations rather than thinking about this mammoth project of wind energy in the north, huge cabling to the south, which loses 30% of efficiency, and then hoping to use the electrical current when it arrives. So do you see a big business model here?
Yeah. In Denmark, we have already 50% of our electricity covered by wind energy. And that calls for some balancing.
Yeah.
And as you say, there are cables to Norway and to Germany balancing a bit. And when the politicians decide for yet another cable to be constructed, I'm like, well, why? Because we can produce hydrogen or even methane from our solid oxide electrolyzers. And this hydrogen and methane can either go into the natural gas grid, which is a really, really large storage capacity, but it can also be stored, for example, underground in caverns, where you can store gas for maybe 3 months of Danish electricity requirements. And when you place that together with a unit that can reversible work as a fuel cell or work as an electrolyzer, we have calculated that turnaround cycle from electricity and back to electricity can be as high as 73%.
Wow.
And that is a potential worth waiting for and going for.
These are game-changing numbers. We're almost out of time, and we still have one important subject to mention. So I don't know how easy this is to do briefly, but you have team projects and partners. Could you just mention who they are?
We work very much in EU research projects and demonstration projects on micro combined heat and power for residential use. We work on showing the hydrogen economy in real life at the Orkney Islands together with ITM Power. And we are invited over and over again to participate in such projects. And we are very pleased in doing that. Then we also work on bilateral terms with industry, and we see this is upcoming. After some years with a little slow business, this is really taking off again, and companies believing in this. Together with us, we are developing next generations. The cells you can get now from the manufacturers, they're good, they're robust, but we continue developing third generation, even fourth generation, bringing costs down, bringing power density up, and bringing efficiency up. So we have to get the technology out on the mass markets now, but we also already now have to prepare for the next generations to improve the technology when it's out there.
And you're the address to go to, of course, because you provide the testing facilities for solid oxide technologies.
Exactly.
And have manufactured them in the past and have a dedicated interest in that since, for decades. It's been a pleasure talking to Dr. Ravn Nielsen, who's Center Manager at DTU Energy, the Fuel Cell Hydrogen Test Center. Get it tested, go to Ava, our message for today. I hope you come back next year and have new announcements about efficiencies and achievements.
I used to come back, and you're welcome at our booth, E57.
Exactly. The booth is over there, E57, Joy Ava there. Yeah. Thank you very much.
Thank you.
And thank you. We'll be continuing in 35 seconds with Rob Castian, who's CEO at Sato International, and they'll be talking about small-scale refueling stations, a fundamental step to commercializing fuel cell transportation. Stay tuned. We'll be back in a minute.